Let me start out by saying that the original version of this lecture was done by Sally Benson, and I stole many slides when she went off to work at the Office of Science and Technology Policy. So she gets credit for a lot of the slides anyway. Anything I say that's wrong is my doing. We need to think about how, not just what the end state looks like, which we absolutely have to get to deep reductions in greenhouse gas emissions, but also the pathway. How do we go from where we are now to where we need to end up? And that has a certain complexity because we use energy that involves emissions in every aspect of modern life. So if you look at the things that we will need to do, well, one thing that will happen, I think, is that we will electrify many energy services. And that means heating and cooling and transportation and those kinds of things. And to the extent that we use fuels for those now, that will lead to reductions in emissions. But there are some of the things that we do now that are where it's either relatively difficult or relatively expensive to change right away from having the CO2 emissions. So one way you can deal with that, and it's not the only way, but one way you can deal with that is to capture the CO2 and put it back in the ground. Now, this can only be one of many things we do. It absolutely is not the solution. It's just one element in the portfolio of how we might deal with this. Let me just say that the ones here that are hard to deal with, Lynn mentioned iron and steel. What happens is you use carbon to strip off the oxygens from the iron oxides. You can use hydrogen. People are working on that. It's still relatively expensive, mostly because you have to make the hydrogen somehow, and that's a possibility. Cement is another place where we make lots of CO2. Cement is made by taking limestone, calcium carbonate, heating it up, and that drives off a molecule of CO2 and leaves calcium oxide. And then, so you get some CO2 typically from making the heat, and you also get some CO2 from the limestone itself. So that's another place where we need to do something. There are some things you can do, but the issue is a real one. And then the most important one really is the intermittency that comes from using wind and solar, and I'll illustrate this in just a minute. So it's power generation on demand, so load following or dispatchable, it's sometimes called. And if you look at assorted estimates that have been made, there are lots of these, and they all vary and largely based on whatever combination of assumptions you make. If you look down there toward the bottom, they're imagining a scenario in which almost 10% of current emissions are captured and stored somehow. To be honest, I think this is a little high. But in any case, we're talking about billions of tons of CO2 to be stored per year in the subsurface. And so we'll ask you toward the end whether that's feasible or not. Is that something that's crazy or not? But the most important part of this slide is if you look at the things that we have to do, improving energy efficiency, using lots and lots of renewables to generate clean electricity, and then a host of other things that can contribute. So the idea of using carbon capture is just one element of that. So Lynn mentioned this question of the wind and solar, and this is another version of that. If you look at, this is a particular day in, I think it was in March of 2017, no, I'm sorry, this is the whole year. And this is the days where not enough wind and solar were available to do a significant fraction of the power generation. And if you just look at the longer duration ones, there were a number of periods of multi-day periods where things like battery storage for electricity just can't deal with the longer time frame. So hydrogen is one element of a way to do this. And maybe you capture CO2 from making the hydrogen, or you do it in some other way. Maybe you use natural gas to generate power, but capture the CO2 there. So this is one way to generate dispatchable power with much lower emissions. Now, and then in the longer term, there are those who are worrying about both the fact that we aren't making progress fast enough here, and the fact that it would be good to draw down the amount of CO2 that's in the atmosphere. We have pushed enough CO2 into the atmosphere now to have significant impacts in the long term, and pulling that down would have some benefits as well. So if you look at the pathways, this plot just shows emissions pathways and the potential ranges of temperature, global temperature increase that might result. If you look at the pathways that get down to somewhere in the 1.5 to 2 degree, even the 3 degree range, they all involve something called negative emissions, which means that we're capturing more CO2 than we make from whatever process it was, and pushing that CO2 back somewhere, presumably underground. So in both the short term and the longer term, there are some reasons to be thinking about this. So why should we do this when there are other things that we could do? And the answer is we need to do all these things. That this is not a simple transformation that we have to make, and it's one where we need all the tools that we can. We can use CCS to reduce some of the hard to reduce emissions. We can enable the long-term removal of CO2 from the atmosphere, provided we get the costs under control. We can reduce the overall cost of decarbonization. Xiaolin showed several slides that showed that it's less expensive, at least for now, to capture some CO2 from making the hydrogen than it is to pay the transformation and efficiency costs all the way through the chain for electrolysis. Now, I don't discount the electrolysis side. There are times if you can make hydrogen locally and transport electricity, we transport a lot of electricity now, and we'll need to do that in big scale in the future. So maybe what you do is you move electrons and make hydrogen where you need it. But right now that still looks more expensive than some of the other approaches. In any case, it's a system, and we have to think about all of this together. So, and then the one last thing is that in terms of accelerating, reducing emissions, these are kinds of things where we have technologies we can deploy today, even as we invent the less expensive technologies that will help us in the future. So, okay, well, at least we should think about this. What would we have to do? Well, there are really four parts. We need to capture the CO2 from wherever it's being emitted, and that usually means a chemical separation of some kind. We need to compress it, and that's really just to reduce the volume so we can transport it. We need some way to get it to wherever it is we're going to store it. That typically involves pipelines. And then the subsurface part of it is the storage. So let me talk a bit about each of these. So the first message is that the lower the concentration, the harder it is to capture the CO2. There's just no getting around that thermodynamically or anything else. The example here is the jelly beans. If you just want the red ones, you have to sort through all the other ones to get to the ones you want, and that costs both energy and then of course that means dollars as well. So if you look at where we make CO2, in in things like hydrogen and ammonia production, they basically are separating the CO2 and the hydrogen already. In other words, they have to do it to get the product that they want. So those are sources now that by the time you get to the end of that process, they've already been separated, so you have the CO2. So an early target for CO2 storage should be those things that are emitting almost pure CO2 now. There's a big project in the Gulf Coast, for example, that is intended to capture the CO2, take the CO2 that's being made in all the refining operations there and store it offshore in the Gulf of Mexico. Then there are the sort of intermediate combustion kinds of things. So if you burn anything that involves carbon and hydrogen, you get CO2 and water and some other stuff depending on whether they're sulfur present and so on. But in any case, when in combustion settings, you're using air as the source of the oxygen, so that nitrogen mostly goes straight through the system, a little bit of NOx maybe, but mostly straight through the system. So you ended up with nitrogen, CO2, and water, and you have to do a separation to get those. So that is more, and about 80% of the emissions that we have of CO2 comes from those kinds of sources. So we really have to, if we're going to do this at any scale, we really have to do it, although we shouldn't ignore the cheap stuff at the top of the slide. And then the last example is the air. So the concentration of CO2 in the air is, call it 400 parts per million, so that's 0.04%. As opposed to something like 5 to 15% in the combustion operations. So that inevitably means that it takes more energy and more expense to separate it from the air. So we should go for all the higher purity sources first before we try to do that. And another way to say that is to look at the thermodynamic work. This is in kilojoules per mole of CO2, and you can see that the amount of work it takes to do the separation goes up pretty dramatically as the mole fraction of CO2, that is the percentage of CO2 in the gas, goes down. And there's no getting around this. This is just the thermodynamics. So how might we do it? Well, okay, so here's an example of, there is a plant, this one is in Canada, and basically what happens is that they stick fuel and air into the boiler, they burn that and make steam, and the steam runs through the turbine, and then the turning turbine makes electricity. So what comes out of that is CO2 plus nitrogen plus water. And the way the separation is done here is you take a solvent. This one is monoethylamine. That solvent likes CO2. So you bubble the mixture through the gas, and the CO2 preferentially dissolves in the mixture. Then you take the mixture off and heat it up to drive off the CO2, and then send the whole thing back, cool it down and send the whole thing back. So it's a big cycle. And you're using the physical separation that comes from dissolving CO2 in the liquid. So solvent-based methods are all some version of this. And if you look at this is a photo of a plant in China that does this. So if you start in the right-hand column, the flue gas goes in the bottom and bubbles upward. The solvent flows downward. And so during that process, the solvent then is saturated with CO2. That goes over to the leftmost tower, and it's bubbled down, and then you heat everything up, and that drives off the CO2. So you can imagine that if it's a good solvent, it really gloms onto the CO2, and then it gives up heat when it does. So then you have to keep things get hot, so you have to cool things down, and you have to do a lot of heat transfer to manage all this stuff. So it's not simple, but it is done every day now at commercial scale, because you have to do these kinds of separations in refining operations. Natural gas sometimes contains CO2, so that's stripped out using typically these kinds of methods. So it is something we know how to do. It's not free, it's not necessarily cheap, but it is something we know how to do. So this is a picture of the Boundary Dam project. That little building over, it's little by comparison with the big power plant, but it's not little. So it takes real equipment and hardware to do all this stuff. It's not something you do at your backyard scale. So what about natural gas? This is that previous one, that was a coal-fired power plant. If you made me guess, I think coal will go away over some time period just because there are all the other issues associated with both coal mining and the other materials that are present in the coal. But natural gas is cleaner to begin with. It has less carbon per unit of energy in the fuel and fewer emissions associated with that. So this is a plant, it's in a little tiny town, Baytown, Texas. It happens to be where I was born. So somehow there's no plaque, though, you know. I'm surprised at that. But in any case, this is a turbine. And basically what they do is they separate the nitrogen from the oxygen. They burn the natural gas with pure oxygen. And so that makes CO2 and water, okay? So you've paid, in effect, for the separation by doing an air separation, not a CO2 separation. But the thing that's useful about this is if you use that CO2 and steam mixture to drive a turbine, then that makes the electricity. CO2 is, even with the water in it, is a lot more dense than steam. And turbines are just a little collection of wings arranged in a circle. The mass flow over the wing is what drives the turbine. So if it's a more dense fluid, then the turbine can be smaller. So the turbine for this little plant was about my size, whereas a steam turbine would be 10 times that big to get the same amount of energy. So then you take the gas that comes out of the tail end of this, cool it down, that knocks the water out. Then you can compress the CO2 and then send that back to the inlet so that the working fluid for this turbine is CO2 plus some water. Now you can't just keep adding CO2 to the system all the time. You have to take some out, right? And you do that at on the high pressure side. So the additional cost of the CO2 compression is already paid. So the additional cost of the CO2 capture is actually quite low here. Now this is in development. They're marketing the things around the world. They claim that they can get to 60% efficiency, which is kind of the range of combined cycle gas turbines. So this would be a less expensive way to capture CO2 using some natural gas. What about air capture? There are teams working on this, and this is a picture of one unit that exists and an artist's imagination of what it might look like at a bigger scale. These are, if you're really going to process a big amount of air from the atmosphere, remember that's the concentration is pretty low. It takes a lot of stuff to do it. So we'll see whether we get there. But there is a project underway in West Texas to do just exactly that. The way this works, this is a process that I'm not going to take you through all of the details, but it uses a potassium hydroxide solution to capture the CO2 and then precipitates that out and makes pellets that they then can make calcium carbonate. And then after that, it's like making cement, so you heat that up to drive off the CO2. Absolutely can be done, and there's a demo plant that does it. Still relatively expensive. And in fact, that group is thinking about making fuels then from the CO2 and some hydrogen. Okay, so we can capture the CO2. There's no doubt about that. Cost is still an issue, but it can be done. Pipeline transportation is the standard way to do this. We've been using high-pressure CO2 for enhanced oil recovery for about 50 years now, so there's a lot of experience with CO2 pipelines, and people know how to do it. There is a project in the North Sea in Europe that is looking at using ship transport of CO2, but really, we know how to do this. This is not a technological challenge. So in that case, what would we do with the CO2? Well, you could imagine that a lot of that carbon that's in the atmosphere actually came from the subsurface, and that's in the form of oil and gas. So one possibility is to put the CO2 back where the carbon came from. And so that's the next idea. And the basic idea here is that you're going to do this at depths that first of all have a seal. So these are rocks that don't allow vertical flow. And you know these rocks exist because otherwise buoyant oil and gas would not be present in the subsurface. So the trick is to find them, and we know how to look for those. And then to do it deeply enough that the CO2 is at high pressure so it doesn't take up too much volume. So seal and depth are the basic starting points. You also have to have rocks that have pore spaces in them. Sedimentary rocks do. And they need to be with easy enough flow through the rocks. This is measured by something called permeability. And if the permeability is too low, as in the seal rocks, then the fluids can't flow, but you're looking for sedimentary rocks underneath those. And there are a bunch of options here. Depleted oil and gas reservoirs are obviously one. The pressures have been pulled down, so it's easier to inject, and there's a lower chance of inducing earthquakes. But oil and gas reservoirs are not distributed uniformly around the planet. So if we're going to do this at big scale, we'd also have to look for rocks that contain salt water now, and those would be a possibility as well. So if you look, this is a geologist cross-section of the Central Valley here in California, Sacramento Basin. You can see all those yellow rocks, those yellow bands. Those are sandstones that were deposited when California was just an imagined set of islands around an arc along the edge. And as California got pushed together, and there was the Central Valley that filled up with a whole lot of sediment, eroded off the Sierras. But what you see here is a stack of sandstones separated by shales. Shales are rocks that are just made from teeny tiny little particles, and so as they get squashed together, they have really low permeability. So these are the kinds of settings where you could put and they do produce oil and gas, so you could put the CO2 and have it stay there. So then you might reasonably ask, okay, will it stay there? And the answer is, if you've chosen well and operated well, then there's a reasonable chance of storing it because there are multiple physical mechanisms. The first is that just the rocks that contain them. The second is that CO2 dissolves in water. You all know this because you drink soft drinks, right? And it turns out that, astonishingly, water that's saturated with CO2 is a little bit more dense than water without it. So now the driving force to go up is replaced by a small one to go down. And then there are various, if you try to push a gas out from a porous medium with water, you end up with a bunch of tiny little bubbles trapped in the pore space, and those bubbles are hard to move, and so that really is permanent as well. And then finally, there is a chance of some rocks will react with the CO2, basalts, for example, and serpentinites that react and make a solid. But most places, we're going to need the other physical mechanisms. So I mentioned the density difference. As you push the CO2 in, then it begins to dissolve in the water, and then that leads to downward flow of that water. It's unstable because it doesn't push the water uniformly, because the little dents, as soon as you have some ripples, then they downward. So these are modeling calculations of what happens when the CO2 dissolves at the top and then floats downward. So you can see that there's a mechanism to retain the CO2 for a long time. So are there enough rocks around the world that we could do this? And the answer is a clear yes. There are plenty of, the dark gray here is basically sedimentary basins that would contain the kind of rocks that you still have to look for seal rocks, and you also have to make sure you're not going to do this in the middle of cities or national parks or that kind of thing. But obviously, it's not the rocks that will limit this. So do we have experience? And the answer is yes. This is a project, Sleipner in the North Sea, that's been operating since the mid-1990s, injecting about 1 million tons a year of CO2 that's separated from natural gas. That CO2, Norway has a carbon tax, and it's less expensive to put this back in the rocks under the North Sea. And we know from doing seismic measurements of where that gas is that it's being retained as expected in the rocks that are there. So we do have some experience with this. There's a project in the middle of the United States, in Illinois, that uses CO2 that's from an ethanol plant. Ethanol, when you make ethanol, you get a nice pure CO2 stream, and that's being injected into rocks there. And that has been, it's been going since 2012 and is doing about 1 million tons a year. I mentioned that CO2 has been used for about 50 years now for enhanced oil recovery. And the reason is that if the pressure is high enough, CO2 will displace oil much more efficiently than water. And you can see in this little micromodel experiment that was done at high pressure. Where the CO2 went, it displaced all the oil. So that means you can recover oil that might be left behind by conventional oil recovery techniques, which are typically based on using something cheap, water, to try to push the oil out. You can do it more efficiently with CO2, and there are projects around the world that do this now. So that actually has given us a lot of knowledge of what happens with CO2 in the subsurface and how that can be put to work for CO2 storage kinds of setting. It's also true that if you take a molecule of methane and oxidize it, at any given temperature, the oxidation makes CO2. At any given temperature and pressure, that molecule of CO2 occupies less volume than the molecule of methane did. So CO2 is always more dense than at the same temperature and pressure. So in principle, you could take the natural gas out, run it through a power plant, make electricity, then put the CO2 right back where it came from, and have volume left over. So you're not going to blow up the system, and actually the pressure would decline. Now that's a gross oversimplification of what would be involved in doing this, of course, but the potential exists to use existing pore space from which we produced oil and gas as a place to store CO2 instead of emitting it to the atmosphere. So can we do this at scale? And the answer is yes, maybe. We do inject plenty of water into the subsurface now, both sewage water and produced water from oil and gas. And we do it at scales that are certainly in the billions of tons per year. So we humans do engineer things at that scale. But I just would note that, this can't be the only thing you do. Because if you take 1 billion tons a year of CO2 and convert it to the typical kinds of densities in the subsurface, that's about 35 million barrels a day of injected in the goofy units that the oil industry uses. For scale, the world uses about 100 million barrels a day. So that 3 billion tons a year that the IEA talked about, that's an oil industry. Okay, so now, right now, there's an issue with how you pay for this. So there's no general carbon price around the world, although there are various versions of prices. But there are some incentives. I'll say a word more about that in a moment. But so can we do this at that kind of scale? Yes, I think physically we can. Will we do it? Depends on how we choose to pay for it. Now, safety is an issue we absolutely have to pay attention to. These are big industrial scale processes. It's not going to, and there's no compromise allowed on safety. We have ways to do this, but it does require paying attention. Some people worry about leakage, and if the site is chosen well and operated well, then leakage can be eliminated. These are high pressure systems, so you can have leaks in pipelines and so on, and there have been a couple of accidents involving that. But those risks can be managed, and they just require careful attention to detail. So if you look at what's going on around the world, there are quite a few projects out there, and I'll just move to this table. So these are results that will be released in a couple of days. I happened to talk to Jared Daniels, who worked for me at DOE when I was there, and he agreed to let me do a quick preview. So I'm not allowed to release this for I don't know, 3 more days. But there's the passage of the Inflation Reduction Act in the U.S. provided some incentives that will help pay for the CO2 projects, and that's generated a big increase. So from 2022, there were 30 operating facilities, and now in 2023, that'll be up to 41, and a whole bunch more planned. So if you look at all the planned projects out there, they would be between 300 and 400 million tons a year. Okay, it's not 3 billion tons a year, but it's a reasonable step along the way. And I'll just let people look at there's a lot going on around the world. It's not just here. There is an effort to think about how to do this at scale. So I'll just finish by stating again why this should be one element in a very broad-ranging portfolio of ways to reduce greenhouse gas emissions. It improves the flexibility, it diversifies the system, and it helps us get there toward the real goal, which is deep reductions in greenhouse gas emissions. So I'll stop there.